I'm going to introduce the tool which is going to help us understand what patterns of inference are valid ones, logically strong ones, and which ones aren't. And this is going to be kind of a chart that we're going to set up. And the chart's going to be, it's called a truth table, and it's set up in the following way. That is, we're going to list, notice, or let me back up. We were talking about P or Q, that is a new proposition that's made up of the connection of two other propositions and one of the logical terms, in this case or. So in this case, and in most of our cases, since the new proposition P or Q is the truth of that proposition is going to be a function of the proposition, the individual propositions of P and Q, we can set out all of the possibilities, and that is all the what you call permutations, the various ways of combining truths and falses in this way. That our first column is going to say we're going to express what could be the truth values of P, the proposition P. Second column, what could be the truth values of Q, and the third column typically is what's going to be the truth value of, the new proposition made by conjoining, by putting together the two propositions and our logical connective. Now notice, as we look at the P column, the column all the way on the left, obviously with regard to any proposition there are only two possibilities. Remember, in our last section of the course we talked about truth, and we had the one truth value principle, that is, a proposition is either true or false. So notice P could either be true or false. Now why have I repeated it? Because we have to make all the possible combinations with the truth value of Q, and in setting up the table, the easiest thing is for P we saw true, true, false, false, and for Q we want true, so P and first row is P is true and Q is true. Second row, P is true and Q is false. Third row, P is false and Q is true. And final row, P is false and Q is false. Now let's go row by row and figure out what the truth value of P or Q is going to be based on what the truth value of the individual components P and Q. So let's look at the proposition at P or Q. Now what's the truth value of either P is true or Q is true in case both of them are true? Well, in case they're both true, remember P or Q is true if at least one of them is true, so both of them are true, so it has to be true. Next row that we're going to look, P is true and Q is false, but notice P or Q says one of the two of them has to be true in order for the disjunction P or Q, disjoining, meaning one or the other is correct. So if P is true and Q is false, nonetheless P or Q is still true. Now if we reverse it, that P is true, or excuse me, P is false and Q is true, since for P or Q to be true, only one of the two has to be true, well, we still have that met, so our third row expresses a condition where the disjunction of P or Q is true in case P is false and Q is true. And finally, our last permutation, our last combination, is that a case where P is false and Q is false. Well, either P or Q is going to be false in that case. And that's, here we have disjunctive syllogism. And notice all of the cases where P is true, where P P or Q is true are the first three cases where at least one of the two is true. And notice if we say P or Q is true, that's what the premise, so it's got to be one of these three cases that we're talking about. Not P is true. In other words, P is false. Well, first row not P is, P is true, so that's not the case. It's not the second row. And finally, we're left with the only row for disjunctive syllogism, which could be the right one, is since not P has to be true, in other words, P is false, and P or Q is also true, well, we now get to the conclusion, Q, notice, is or has to be true in this case. So the truth table tells us very specifically that the pattern of argument that we know as disjunctive syllogism or argument by elimination is a valid argument. It's a truth-preserving argument. So you see now how the truth table will help us understand which patterns of arguments are good ones, which are bad ones. I'm also going to show you a way later on, at least for conditionals, of using kind of the circle diagrams that we used in predicate logic to understand the fundamental inferences and why these are valid patterns of arguments. But let's move on and take a look at conjunction, the AND operator, P and Q, and there are two good inferences. That is one called simplification, that is if both P and Q are true, then Q is true. It could have been P. And working the other way, if we start from the premise that P is true and number two that Q is true, P and Q will both be true. And again, we can look at the truth table set up exactly the same way, except now we're looking in the third column as being P is true and Q is true. Now if P is true and Q is true, P and Q is, that's right, also true. Now if P is true and Q is false, the proposition that P and Q are both true is false, right? Because both of them have to be true for P and Q to be true. And if P is true and P is false, as in row 3, and Q is true, well, P and Q has to have both of them true. So again, in this case, P and Q would be false. And if both propositions are false, both of them can't be true, so it again has to be false. So notice the only case in which you have P and Q being true is our first case, which explains simplification. That is, if we know that if P and Q, that premise is supposed to be true, and the only place it's true is that first row, we can conclude that Q is true. Notice we could also conclude that P is true. Or going in the other direction, if our premise, if we have P and Q as premises, we want to look for a case where P is true, and Q is true, the first column. We also can conclude that P and Q are true. Now notice the truth table doesn't tell us whether P and Q are in fact true. It says for any P and any Q, these are the relations that hold between the truth values of the components, the individual P's and Q's, and the truth value of the new proposition that's made by conjunction, P and Q. Now let's look at negation for a second, or let's look at something called, double negation. from the fact that P is true, we can conclude that it's not the case that not P is true. And the way you can see that is P is true means not P. Look at our circle and the square around it. The square being cases where not P, everything other than P is true, and inside the circle, cases where P is true. And let's look at the truth table. And truth table here is going to be a little simpler because we only have one proposition P, so it's either true, or it's false. And if P is true, well, think about it, not P, it has the opposite truth value, false. And if P is false, not P has the opposite truth value, true. And if we negate it another time, if we put it in the other column, we'd see that it would look exactly like the P column, which is why double negation works. Even though in English they say there is no such thing, or it's grammatically, I should say there's no such thing, it is grammatically incorrect to use a double negative.